or keeper than a physicist, but okay, thank you to organizing committee to inviting me. And I will talk a little bit about our work in Alagoas University. And the main topic of my talk is about topological valence in nematic shells, but nematic shells with an anisotropic shape. Okay, this is my co-works. This ballet dancer is Elena. In free time she's a PhD student, and Catarina, it's a graduate student. Professor Leonid Mirantsevi, and Marcelo Lira, it's a professor in the same institute of me. Okay, as we know, a natural way to induce topological defects in liquid crystals is to confine them in a specific geometry. If you confine it in a spherical geometry, you can induce two types of defects. If this spherical geometry has an isotropic, homeotropic anchory, you have a point-like defect in the center of the sphere. But if you can also induce a defect line around the sphere, and you have like a Saturn ring in your nematic drop with a spherical shape. Okay. And in 2002, David Nelson suggested that you can use nematic drops, but with like a nematic shell, to build as a building blocks to explore the tetravalence logical diff as a chemical building blocks. In this case, we have here two pairs of bosons, and we have four valence spots, as you can use to fusionalize with a polymer and induce complex structures with this nematic shell. Okay, but we have here two initial problems. The first one is how to produce nematic shells. And the second one is how to manipulate the shells to overcome the temperature effects. Because if you think if you have a nematic shell in a solution, maybe the Brownian motion will destruct your specific configuration that you need. So the first problem was solved by a group with David Weiss and Fernand's lab in Georgia Tech, and they use a microfluidic device, as Zola has presented here, and to induce a drop of water encapsulated with a nematic top. Okay, here we have a liquid crystal. Here a liquid crystal. Here is a water solution with surfactants. Here it's another solution of water solution with surfactants. So this the injection of the water solution here drags the nematic and produce a nematic shells around this water drop. Okay, and this procedure is very interesting because if you control the concentration of surfactant, you can control the anchoring in the nematic shell. If the concentration is very high, you can induce no homeotropic anchoring, but a degenerate planar anchoring. And if you have a specific concentration, here you can induce the internal shell has a planar anchoring, and the external shell may have a homeotropic anchoring. Okay, and in 2007, they observed this three types of structure of spherical nematic shells. Here, this is the bright image. Here's the cross-polarized image. And you can see here, in the first one here, A and B, you have 4 defect points, like predicted by Nelson. But also, they observed the emergence of another type of structure with 2 defects. And this 2 defects satisfies the Poincaré-Hopps theorem, which restricts the direct configuration to a topological charge of 2, plus 2. So here we have 4 defects plus 1/2. Here 4 defects plus 1/2. Here we have 2 defects plus 1. And you can also observe here a structure with 3 defects, but this is a plus 1, but here we have 2 plus 1/2. And this is very interesting because this structure and this structure may be reproduced by theoretically, but this structure here, no. We cannot observe in any simulation or any theoretical model cannot explain why this structure is observed. And it's more interesting because this structure has the same probability to be observed as these two. This is you can see this argument in this recent paper here of 2016. Okay, as we have said, we can observe these 4 types of structure. This is a PRL of Claudio Zanoni, and he shows that he can obtain with dynamic simulation, Monte Carlo simulation, the configuration of 4 plus 1/2 defects with a tetravalent behavior with a tetragonal configuration. And if you can apply a electric field, you can change this topological valency for 4 valency hotspots to 2 valency hotspots with change these 4 defects of plus 1/2 to 2 defects of plus 1 topological charge. Okay, but Professor Mirante and Professor Viga have studied another structure with a sphere, and this sphere has a equatorial belt where the direction of the director is fixed along the hemisphere. So in this case, they observe the emergence of a vortex inside of these shells, and it's a different configuration. It's a very different configuration of the predicted of Zanoni and observed experimentally. And also, Napoli-Vergoli shows that if you can control the intrinsic and extrinsic curvature of these shells, you can change the nature of the nematic alignment in these shells. It's a very interesting paper. So, in 2014, Nuno Silvestre and co-works shows that you can control the nematic colloids with using a trapezoidal trap. So this pyramid here can be used to trap this colloid, and by trapping the colloid, the defect point. So you can manipulate now these structures with a potential. So you can withdraw with thermal fluctuations. So you can now control the spheres with a defect, and you can use this trap to manipulate and produce a nanostructure as you wish. Okay. In 2015, my group was studying nonlinear optical effects in liquid crystals containing gold nanoparticles. Okay, and during the TMI measurements, we observed that here we have nanorods, but if you can see here, we have a small shell around the nanoparticles. Okay, as we know, we need to dry the grids before you take the TM image. So this is a nematic shell around the nanoparticle. So what's we ask, what's the nematic configuration around these nanorods? Okay, so this is three good questions. What's the nematic configuration around the nanorods? How many topological defects will be observed in these systems, and how the electrical field can change this configuration. So we use molecular dynamic simulation to study this system, and we use a simple scheme. Here we have ghost particles as the external layer, and we have here, we call that also ghost particles as the internal layer. Between them, we have our nematic liquid crystal with 3 degrees of orientation and translations. This ghost particle has center of mass fixed and orientation fixed. So you can, this ghost nanoparticle has a homeotropic orientation, but the interaction with these particles here is favors a planar degenerated configuration. Okay, this is the potential that we use it with Lennard-Jones to account the isotropic contribution, and the modified version of the Meyer-Salp model to account the anisotropic configuration. You have this parameter here. If you have the interaction between molecules inside the nematic shell, it's the parameter, this parameter epsilon iso. It's positive if you are looking 2 particles interact inside the nematic shell, but it's negative if you have a particle interacting with ghost shells. So this contribution here gives rise to a planar degenerated configuration in the shell. Okay. Okay. We use around 7,000 steps to perform the molecular simulation, but we can change this to around 110,000 steps, and we compute all the parameter to verify the organization of the system and to achieve the equilibrium configuration. Here I will show you a little movie. Here we have the North Pole and the YZ projection. Okay, let's start again. We start with a random configuration, then the system will evolve until reach equilibrium configuration here. Okay, if you see, these are the equilibrium configuration of the North Pole and the YZ projection. In the North Pole, we observed the emergence of 2 defects with a +1/2 charge. In this way, the North Pole has one topological charge +1, and the South Pole has the same topological charge +1. In this case, the spherocylindrical shell should have a plus 2 topological charge as expected by Poincaré-Hopf theorem. But we observe here, in this case, we observe the emergence of two defects around the change of the cylindrical part to the spherical part of the spherocylindrical. These two topological charges has opposite signs. This has a minus 1/2, and this is plus 1/2. And these two pairs are two pairs of topological defects metastable. They are metastable. If you change the initial condition of your simulation, these topological defects will emerge in another position of your spherocylindrical, or even they cannot be observed. So this result shows that you can obtain different topological valence in a spherocylindrical shell. Okay, this is very different from the spherical shell, because in the spherical shell you have only three configurations. Maybe. In this case, no. In this simulation, no. But if you run another simulation with a different initial condition, these defects may change the position. So valence 8. 4. 2 plus topological charge is plus 2. Topological charge is plus 2. But yes, because these two annihilates the charge. These two annihilates, but in north pole you have plus 1, and the south pole you have another plus 1. Oh, so just north pole. Just north pole. Yes, is hidden. Is. Yes. Yeah. Okay. And in this figure C, we have the account of topological charge with using the tensorial order parameter. We can compute it. This is the project. This red one is the plus 1/2, and this blue one is the minus 1/2. Yes, I will show the next slide. So we compute the order parameter here, and here we can see if you slice this north pole in 18 parts, you can see here the order parameter has a minimum in these positions, angular positions here, indicating that we have literally 2 plus 1/2 in the north pole. Now I will show you, as Antonio asked, the effects of the aspect ratio. We change the internal radius of the spherical part and the height of the cylindrical part. And if you here, obviously, 8 over R in, we have only a sphere with 1 plus 1 charge here and a plus 1 charge in this position. But if you change a little bit the geometry of your shell, the topological, metastable topological charge appears here. This is a minus 1/2. Okay, and the plus 1 is in this position. If you change again, it's important to stress here, it's this topological, metastable topological charge appears in pairs. Okay, they appear in pairs. Here, keeping the topological charge of the spherocylindrical shell as +2. Okay. If you change more the configuration of your spherical cylindrical shell, you can obtain this even the topological. This is important because if you hear this, the initial configuration, this simulation is different from this and different from this, and the position of the topological defect change. Okay, this +1 and +1/2 and -1/2. Okay, now we investigate the effects of the electrical field, and we use a contribution to the potential of the electrical field with polarizability of using the molecular polarizability. Okay, we investigate two configurations: a longitudinal parallel to ZX and a transversal field perpendicular to the ZX. This is the simulation of longitudinal electrical field. Here we have the initial configuration of without the field. Now we apply the field and you can realign. We change the configuration of the nematic director, and it's important that when you apply the field, the topological metastable topological defect disappears. Okay, only +1/2 here, +1/2 in the south pole. And this is the final configuration. If you apply a stronger longitudinal field with +1 charge here in the top, north pole, and +1 in the south pole. This is the equilibrium configuration if you increase gradually the field and decrease the field. This is the configuration. It's difficult to see here, but a small field suppress the emergence of this metastable topological charge. So you cannot observe this metastable topological charge here close the spherical cup, and we have this final configuration with just two defects in the one defect in the north pole and one defect in the south pole. Now let's see the come back, but in different positions. Yeah. 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 Because the position of these defects are not fixed. It's an important question because there is a work of Virga that shows that if you have a shell with a change in the curvature, this change of curvature will induce the emergence of metastable defects. This is a terminology of him. It's just replicate, but in my opinion, this configuration does not correspond to may not correspond to a equilibrium configuration if you run this simulation around the 1 million steps. Maybe disappear. The thermal fluctuation induces the annihilation of these defects, but it's important to stress the equilibrium configuration needs to have a topological charge equals to +2. Maybe not. Maybe just a minimum of the energy, but that is not, is may not correspond to the global minimum, and we need to run or increase the temperature to annihilate the emergence of these defects. This is it's not a closed question, okay? It's I yeah yeah yeah. Wait wait yes. No, because this is not continual theory. It's a molecular dynamic simulation. In the continual theory, you have a large number of molecules. Then you consider that each point of continual theory contains a large number of particles. Here, no. Here we have a final number of particles. You cannot use Alaska theory to study this. I will show you. Okay, let's continue. This is the transversal field. It's very interesting here. Please pay attention in this region, okay? Now it's the transversal field. Do you see? Oh, you start again. From the beginning. Random configuration. Now you have closed equilibrium configuration. Okay, 2 plus 1/2. Now we apply the field. Do you see? These two defects are part away from each other. Okay, they split and they migrate to this region here of the spherocylindrical. Okay, and we have here 2 plus 2 plus 1, 2 plus 1/2 charge here in this position. Okay, so if you can control the direction of the applied field, you can control where the hotspots appears. Okay, it's important because if you apply the longitudinal field, you have just one hotspot with topological charge +1, and if you apply a transversal field, you have 4 hotspots with +1/2 charge. Okay, and this is the equilibrium configuration, and what is this? We can now play Tetris. Okay, you can change the position of the hotspots, and maybe you can control the formation of building blocks of spherical nanoparticles with different topological charge, similar to the result of the Rafael Zolla. But in this case, we use a nanoparticle surrounded by a nematic shell. Okay? But how to produce these spherical cylindrical nematic shells? Maybe in the original way, you use the water injection to produce the nematic shell. Maybe we can use electrophoresis to produce a shell of nematic part, a nematic liquid crystal around a gold nanoparticle. Okay, and a similar result was obtained in the last year. In this case, they obtain a spherical shell around a ellipsoid nanoparticle. This is a paper of soft matter, and they observed interesting topological configurations. Okay, it's another group. Okay, and our collaboration in Alagoas University performed the synthesis of nanoparticles with like a bone. Okay, and this you can see here. here we have like a spherical part. Here, this spherical part has a positive Gaussian curvature. This part here is cylindrical, so it has a no Gaussian curvature. But in this part here, we have a hyperbolic configuration with a negative curvature. So you can use this nanoparticle to induce the formation of another kind of anisotropic shell, nematic shells, but using as a core with like a dumbbell-like core. Okay, and we use we produce a dumbbell-like surface using this surface revolution here, and we study this configuration specifically. We have here a cap with a positive Gaussian curvature, and here we have a central part with hyperbolic geometry with a negative Gaussian curvature. Okay, this is the slice of our shell, a thin slice, and here we have the equilibrium configuration. Here we have a +1, only a +1 defect, not 2 +1/2, but just one defect here, and defects disappear. Okay? But let's investigate the effects of the electric field. This is a preliminary video because we need to insert more frames to produce a video with a better resolution. I'm sorry for this, but it's the best I can have right now. Let's see this random configuration. You can see the director. The field is null. This is wrong. It's 0.1. Oh, see, the metastable defects appears here and here in the negative part. But it's interesting if you apply a large electrical field, two line defects appears in the position where you have the change of the curvature. Here the curvature changes from positive to negative. And this position have these two lines of defects. If you keep increasing the electrical field, this line position disappears and we have the typical orientation of a spherocylindrical shell. Okay, let's see here. If you wait a little bit. And you can see, okay, disappear. This is the configuration of we have here the initial configuration without electrical field, and when you apply a small electrical field, the metastable defects appear here in the spherical part, but here the +1 keeps. I'm not sure because it's the same configuration. It's another. There is no additional information if I show this part. And if you keep increasing the field, the metastable defect disappear, but this region try to keep the orientation around the equator of the shell. If you keep increasing, the center part is reorientated by the electrical field, but in the position where you change the curvature appears these two defects lines. Okay? And if you keep increasing, these two defects lines disappear. This is the configuration if you apply a transversal electrical field, and the behavior is similar to the spherical cylindrical shell. Okay, and if you keep applying, the +1 are migrating to this region here. Okay, and it's important to stress that you cannot have a migration of the topological +1 topological charge to this part here, okay? Because the negative curvature acts like a potential, a repulsive potential to positive defects. You cannot have positive defects in the region of negative curvature. The +1 are here. In this part, we have no defect. Okay. Also, we investigate if you insert a cylindrical part in the middle of the dumbbell. You have a positive curvature, negative curvature, and zero curvature. And again, in the zero curvature appears the metastable topological defects. Okay? And here again, if you apply the field, the small field annihilates the topological metastable topological defects in the cylindrical parts, but there is an emergence of new defects here. And if you keep increasing, you can have two lines where the curvature changes from positive to negative, and then they disappear. So in summary, we have studied very different configuration of nematic shells with an anisotropic shape, and I would like to thank the agents of Brazilian agents and the INCT, and let me talk a little bit about our university. This is our university is not here, but it's close to here. Okay, it's in Maceió. It's a very beautiful city. Okay, more beautiful than Natal, I think. Here, okay, here we are here in Natal, and Maceió is here. Okay, it's a very interesting place, and our group works with different systems, with ferrofluids and luminescent polymers, and this is a picture of Z-scan Antonio shows yesterday, and if you want a little bit more about our work, this is Alice, and thank you for your attention.